In this video we're going to learn about analyzing crystals using X-ray diffraction. But first I want to give an overview of materials characterization techniques. I'm going to start off with microstructural characterization. So the technique for that is to take the sample you're interested in, cut it, mount it in plastic, polish, and then etch to reveal features. Cutting is normally done using a diamond wheel, but for very hard samples we may use a technique such as electro-discharge cutting, where a moving wire with a high voltage on it erodes a sample basically by arcing against it. Samples are mounted using typically a two-part resin. It's also possible to use bakelite. Here we see some molds used for mounting samples, and over here we see some samples that have been mounted and then ground to reveal the cross-section. First there is initial grinding to get a flat surface, and then the surface of the mounted sample is polished to about a 1 micrometer level. It is now ready to be looked at under a microscope. Metallurgical microscopes have their light source at the top, and the light comes down here and is diverted using a beam splitter down to the objective. The reflected light goes up and then to the eyepiece. Here's an image of looks like aluminum, a polycrystalline aluminum. The colors are due to the use of polarized light, and the contrast in these images is due to different phase compositions and also different orientations of crystals. It's also, scanning electron microscopes are also useful in microstructure analysis. One excellent thing about electron microscopes is that when the electron beam impinges on the particle, X-rays are created. The spectrum of the X-rays that are produced by the interaction of the electron beam with the material can be used to identify the material. So for instance, an electron beam can be focused on one area of the sample, say this dark area, and by looking at the spectrum of the X-rays we can identify that, for instance, here we have calcium present there. I think the dark area is actually magnesium and the light areas are calcium. Again, when we look at an image, we need to understand why and how contrast is created in the image. The reasons for contrast in a scanning electron microscope image would be different than the reasons for contrast in an optical microscope image. In a scanning electron microscope, something I didn't mention is that the electron beams are coming from the top, impinging on the sample, and then the scattered radiation is being measured as the beam is scanned over the sample. In transmission electron microscopy, the electron beam passes through the sample and then the transmitted beam is monitored. Transmission electron microscope requires very thin specimens, and there are special techniques for producing extremely thin sections. It's also possible to obtain diffraction patterns that allow the crystallographic lattice of the sample being analyzed to be studied. Scanning tunnel electron microscopes can be used to look at the surface of samples to a very high resolution, allowing individual atoms to be resolved. The way it works is that we have a tip that is picking up the electric field from the surface. The tip is scanned using a piezoelectric actuator which moves the tip over very small distances, and by looking at the corresponding tunneling current and plotting that as a function of the position of the probe, we can obtain images like this, for instance. This is a scanning tunnel electron microscope. It's pretty small, and not only can atoms be resolved, the technique can also be used to move atoms on a substrate. And here we see IBM, they've written their name or their logo in atoms using such a technique. The technique that we're going to focus on today, X-ray diffraction, involves mounting a sample at the center of a equipment such as the one pictured. The sample may be powdered or a single crystal. We have a source of X-rays coming in. The X-rays reflect off and are picked up by a detector. The detector scans over a range of angles. If we plot the intensity of the X-rays received as a function of the angle that the incident and the reflected beam make, we get a plot showing that at specific angles we get strong reflections. The distribution of the strong reflections as a function of angle can be used to identify the specimen. It is also possible to use neutrons to perform diffraction experiments. This requires a very large facility, and neutrons penetrate deeper into a sample and gives one a better representation of the bulk of the sample. Let's come back to X-ray diffraction. The purple represent atoms in a crystal, and we can identify sets of planes that could describe this crystal. If we have an X-ray beam incident on the sample from a certain angle, a reflected beam or a diffracted beam has a strong intensity when this relationship, called the Bragg relationship or Bragg's law, is satisfied, where D is equal to the interplanar spacing theta is the angle indicated on the diagram. It's the angle between the surface and the incident beam, and the angle between the surface and the diffracted beam, both of these angles being equal and given the symbol theta. N is an integer and represents the order of the reflected ray or the diffracted ray. Usually, the intensity of the beam reflected beam reduces as the n increases, and typically in experiments n is always equal to 1. The other parameter is lambda, and that's the wavelength of the incident X-rays. So this is an interference effect. The X-rays coming in, they excite all of these atoms to emit X-rays, but what happens because of if we consider the X-rays as waves, we can see that we get interference effects and we only get constructive reflections at particular angles, which are predicted by Bragg's law. Okay, so let's see how this applies to crystals, and we're going to look at simple examples. So X-ray diffraction with cubic crystals. So we know that n lambda is equal to 2d sine theta. We're going to do our experiment and we're going to find the angles theta at which we get strong reflections. What can we do with this information? Well, we know that n equals 1, and so the equation goes to lambda equals 2d sine theta. We also know that for cubic crystals, or cubic systems, we know that d is equal to a naught, the interplanar spacing, divided by h squared plus k squared plus l squared, the square root of those, where h, k and l are the Miller indices of the set of planes. And a naught is the lattice parameter, or a sub 0 is the lattice parameter. Now, if we square equation 1, we get this. And substitute in, so this is squaring equation 1, and let's square equation 2 as well. D squared is equal to a naught squared h squared plus k squared plus l squared. So call this 3, 4. Now if we substitute d squared in equation 3 from the value of d squared in equation 4, so we're substituting 4 into 3, we get lambda squared is 4 a naught squared sine squared theta h squared plus k squared plus l squared. So we can see that sine squared theta is going to equal lambda squared over 4a naught squared h squared plus k squared plus l squared. We recognize, excuse me, sorry about that. Oh, there we go. We recognize that this part here is a constant. Because the wavelength of the radiation is fixed, we're using a monochromatic X-rays for this type of experiment, A0 is the lattice parameter that is fixed. So this is the constant. So we can see that sine squared theta is proportional to the sum of the squares of the Miller indices of the plane that from which the reflection has come. If we knew what the Miller indices were, we could then figure out the lattice parameter from X-ray diffraction experiments. In this article by Dr. Scher, he outlines that the H, K and L values have to have certain, there are certain conditions on the combination of H, K and L for different crystal types to give a reflection. So these are selection rules. In a primitive cubic, all possible values of H, K and L are possible. So we can have, for instance, 1, 0, 0, 1, 1, 0, etc. And that means that H squared plus K squared plus L squared can have values 1, 2, 3, 4, 5, 6. Notice that 7 is missing. 8, 9, 10, 11, 12, 13, 14, 15, there's no 15, etc. So notice that 7 and 15 are missing. And these can be used as clues to determine what kind of crystal structure we have. For body-centered cubic, reflections are only allowed when H plus K plus L is even. Reflection is not allowed when H plus K plus L is odd. So we're only going to get reflections from 1, 1. Let me write these in the proper. So here we had 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, etc. Over here, for body-centered cubic, H plus K plus L must be even. So the first one we can start with is 1, 1, 0. Another one is 2, 0, 0. So this will give us a sum of H squared plus K squared plus L squared of 2. This will give us 1 of 4. So we can see here that 1 is missing. In this series of H squared plus K squared plus L squared, we can see that 1 is missing. 1, 2, 3, 4, 5 is missing, 6, 7 is missing, 8, 9 is missing, 10. So basically they're all even numbers. 2, 4, 6, 8, 10, 12, 14, 16. Yeah. So they're all even. Face-centered cubic, reflections are only allowed when H, K and L are either all even or all odd. So let's look at some examples. 1, 1, 1 are all odd. 2, 0, 0, all even. And we could continue like this. And if we do that, we get this sequence of possible values of H squared plus K squared plus L squared. There is no 1 and 2. Okay. So just to clarify, this is the missing list for the previous case, body-centered cubic. In the face-centered, there is no 1, there's no 2, there's a 3, 4, there's no 5, there's no 6, there's no 7, 8, there's a missing 9 and a missing 10, etc. So this gives us some clues of how to identify crystal structure together with this equation here. So let's do an example to illustrate or to demonstrate how to apply what we've just learned. Let me just take a copy of this equation. Okay, let's have a look at this example here. The results of an X-ray diffraction experiment using X-rays with lambda equals 0.7107 angstroms, a radiation obtained from a molybdenum target, shows that diffracted peaks occur at the following 2 theta angles. I just want to explain what this means about the molybdenum target. One can obtain different frequency or wavelength of X-rays by using different targets on which an electron beam is directed onto. So molybdenum gives a characteristic X-rays of this wavelength. There are further filters to, if necessary, to filter the X-rays coming from the target to produce a monochromatic source. So here is the experimental data. These are the peak numbers. These are just sequence numbers. The first peak occurs at 2 theta, 20.2, second peak 28.7, etc. Determine the crystal structure, the indices of the plane producing each peak, and the lattice parameter of the material. Okay, how are we going to do this? Well, the first thing that we want to do is, or the easiest thing to do, is to use a spreadsheet to analyze this data. But first I'm just going to step by step tell you what we're going to do. So the first step is we want to apply the equation that we just derived earlier on. This equation. You see that this is the angle here is theta, but we're given 2 theta. So the angle in the equation is theta, but the angles given typically from the experiment are 2 theta. So what we need to do is first calculate sine squared theta for each data point. So once we've done that, we realize that they're going to form a series. And this part increases according to an integer level. So what we're going to do, we're going to divide sine squared, our table of values, by a common denominator to transform the list of sine squared values into a list of integers. It'll be easier once I show you how to do that. Easier to understand once I show you an example. So I've opened up an Excel spreadsheet and I've entered in the data in the problem. This is the peak number, and I've entered in the 2 theta value given in the problem. So our first step is to calculate sine theta squared. I'm going to put in the equation sine. We have to be careful here because Excel expects the argument of the sine function to be in radians. So we have to convert to radians. But first, we must take the 2 theta value and divide by 2 to give theta. To convert to radians, we multiply by pi and divide by 180. That gives us sine theta, and now I need to square that value. This gives me a list of sine theta squared values. Now, I know that these are proportional to h squared plus L squared plus h squared plus k squared plus L squared. So what I'm going to do now is I'm going to normalize those values. What that means is I'm going to pick the lowest value here. I'm going to divide all of them by that. So this, the normalized value, this is going to equal this divided by itself. Now, I always want to divide the rest of these numbers by the lowest value of sine squared theta. So that's why I put these absolute symbols in. Okay, so as we expect, 0.03075 divided by 0.03075 is 1. Let's copy this equation down, and now we get the ratio of this sine squared theta value to the lowest value of sine squared theta, and we see a pattern. Now remember, this is experimental data, and if we were actually do this experiment in the lab, we would not get exact integers here. There is always some experimental error in the measurement of the theta angle. But we can now look at this. So let me just expand this out, and we can try to guess the pattern here. What's the approximate value? And this would be maybe a bit of a trial and error. We have a 1, 2, 3, 4, a 5, a 6, a 7, and an 8 sequence. Now, what kind of crystal structure could produce such a sequence of 8 squared plus k squared plus L squared values? Well, let's have a look at the selection rules again. So the selection rules tell us that we can have a sequence of 1, 2, 3, 4, 5, 6, but the 7 is missing for a primitive cubic cell. So the sequence we've got doesn't match because we have a 7. Let me just go back to show you that. We have a 7, so we cannot have a simple cubic structure. Could it be a body-centered cubic? Well, body-centered cubic is 2, 4, 6, 8, 10, 12, 14, 16. However, if we say that the first normalized value corresponds to a 2 rather than a 1, if we divide each of these values by 2, then we do indeed get a sequence 1, 2, 3, 4, 5, 6, 7. That includes 7. So I'm thinking it must be a body-centered cubic. If we look at the face-centered cubic, we should get 3, 4, 8, 11, 12, 16. This pattern is not really matched by what we have. So I'm thinking it's the body-centered cubic. And if that's the case, this is not really worth a value of 1. in terms of h squared plus k squared plus l squared, this is actually worth 2. So all we do is, when we do our normalization, we normalize the first value to 2, so it's multiplied by 2 there, and now I get a sequence of, in fact I could just reduce the precision of this number here we go. There we go. 2, 4, 6, 8, 10, 12, 14, 16. This is the sequence that we would expect for body-centered cubic. So we could now index these peaks and determine of what form, that's the direction. Ah, made a mistake. Should have used curly brackets. So okay, so HKL forms. There we go. So 2, this is telling us that h squared plus l squared plus plus k squared equals 2. Now let's have a look at the selection rules again. And we see that for body-centered cubic, reflection is allowed when the sum is even. Okay? So, alright. So we have 110. This must be the 110. This must be, it can't be the 111. So this must be the 200 peak. 6. How do we get a 6? So we could have a 211. 8 is 220. So if we square each of these and add it to the next, we get this value here. So I could actually relabel this column let's leave it as that. So that's supposed to mean h squared k squared l actually it's h squared plus k squared plus l squared. That's what that's supposed to mean. Okay. So 10, how do we go to 10? That will be a can't be a 4. 4 plus 4. So we could do a 3 and a 1. Three 10, because the total is even. A 12 is 222. 14, if we want a 14, we could do a 3, 1. That's 4 and 2. Actually, that's 14, yeah. Because 9 plus 1 is 10. And then the 16, we want, how do we get 16? We could do a, if we do a 3 we get a 9, that will leave 7 left. That's probably not right. Let's do a 4, of course, 4, 0, 0. There we go. Okay. So now what have we done? We have determined the crystal structure. Okay. So lattice type, body center cubic, and we've indexed each of those peaks. We know from which set of planes each reflection comes from. So now we have this information, we can actually determine the lattice parameter, and I'll show you how. So let's just reiterate what we just did. We apply this equation, we calculated sine squared theta for each data point, we normalized sine squared theta table, and compared to selection rules, to identify crystal type or lattice type. Once we did that, we were able to index peaks. Now we can determine A0, and the way we do that is let's find sine squared theta for peak 1. We know the wavelength. We want to find A0, but we know, because we indexed the peaks, we now know what values of H, K, and L correspond to this angle, and we can solve for A0. So it's very interesting. Let's try another example. Here, figure 3.4.3 shows the results of an X-ray diffraction experiment in the form of the intensity of the diffracted peak versus 2 theta diffraction angle. If X-rays with a wavelength of 0.15418 nanometer are used, determine A. Let's look at another example. The figure below shows the results of an X-ray diffraction experiment in the form of the intensity of the diffracted peak versus the 2 theta diffraction angle. If X-rays with a wavelength of 0.15418 nanometers are used, determine A. the crystal structure of the metal, B. the indices of the planes that produce each of the peaks, and C. the lattice parameter of the metal. The technique is extremely similar to what we just did before, except now we must read the 2 theta values off the graph, and in doing so we realize that in practical X-ray crystallography that there is an uncertainty involved in determining the center of the peak. And because each peak has a width that is dependent upon a number of things, including how finely powdered the sample is. So, okay, let's. There's 1, 2, 3, 4, 5, 6, 7, 8 peaks. The first peak occurs at 17 degrees. The second peak 20.5. The third peak occurs at 28.5 degrees. The fourth is, looks like 33.5. The fifth is 35.5. Sixth at 41. The seventh at 45. And the eighth at 46.5. We're now going to put these numbers into a spreadsheet. There we go. This is the peak. This is 2 theta. First angle is 17. Second one is 20.5. Third one is 28.5. Fourth one is 33.5. Sixth one is 41. Sorry, that's the fifth one. Was, I think they've missed one. Let me have a look. 17, 20.5, 28.5, 33.5. Oh yes, the 35.5. Sixth one is 41. The seventh one is 45. Eighth is 46.5. There we go. Now we are going to calculate the sine of theta and square it. So that's going to equal sine. This angle is 2 theta, to divide by 2 to get theta. And then I'm going to convert to radians as Excel defaults to radians. And then finally I'm going to square that quantity. Oh, damn. Probably put the wrong brackets in. There we go. Copy that down. Okay. Now I'm going to normalize these results in order to convert them into integers, and I'm going to use the sequence of integers to identify the crystal. My first attempt is to divide all of these numbers by the lowest of the series, which is the first one. And to do that easily, I'm going to use absolute cell reference. So as expected, this has an integer value of 1. I'm going to copy down. Let's have a look at the results. 1.4, okay, not an integer. No, not an integer. Could be close to a 4. That's close to a 4. Not really. Okay, this is not, doesn't look very good. Yeah, it doesn't really seem to follow any pattern. So why don't we look at the selection rules again to see what it could be. Perhaps we could try this, normalize the first number to 2 and see if we get a sequence that looks like this. However, I don't think this will work because had we normalized the first number to 1, we should have got a sequence 1, 2, 3, 4, 5, 6, and includes 7, indicating it's not a primitive. So I think that the best fit might be offered by this, by assuming it's phase-centered cubic, in which case we need to normalize this first number to a 3. I'm going to multiply that by 3, the equation by 3, and that's equivalent to dividing all of these numbers by the third of the first number. Okay, getting something closer, but remember there is experimental error, and we may have made some errors in reading the values off the chart, so we're not getting precisely integers. So okay, so we're going to, if this is the FCC sequence, we get a 3, then a 4, then an 8, that's believable. Oops, excuse me. There we go. 11, yep, believable. It's supposed to be a 12, it's a little bit on the large side. It's supposed to be 16, a little bit on the large side. That's supposed to be a 19, and that's supposed to be a 20. So maybe it had some, if we went back to the graph and read it more accurately, we should hopefully get a sequence that is similar to this. But I'm convinced now that this is a FCC type. And we can identify the first, with FCC, the first peak. To identify it, first let's have a look at the selection rules. For phase-centered, reflection is allowed when H, K, and L are either all even or all odd. You may be wondering how these are calculated. It's calculated using a process called calculating structure factors. So this tells us the intensity of the reflection is the function of angle. So if you look up structure factors, you see how these are calculated or determined. But getting back to this, we know that the indices for the first possible reflection is going to be 1, 1, 1. So all the Miller indices are all odd, and the squares add up to 3. This is supposed to be a 4, so this must be 2, 0, 0, as all the numbers are even. And the squares are up to 4. This is supposed to be an 8. 3, 4, 8. So that's 2, 2, 0. All even. Squares add up to 8, etc., etc. Now we know the what the H, K, and L values are for this first row. We can plug the values into the equation that we derived earlier. Let me show you that equation. Oh, okay. Sorry, I changed the slide I was on. But the equation that we're going to use is H squared plus L squared plus K squared is equal to 4A0 squared over lambda squared times sine squared theta. When I presented this equation earlier on, I may have move this constant to the other side. But now we know, for instance, for the first peak, what H, K, and L are. We know lambda, it's given, and we know theta. We can calculate A0.